Assalamu alaikum. Today we'll continue talk about electrical circuit 2 and we'll talk about chapter 17, which is about series parallel AC network combination circuits. We'll study some examples only. And in chapter 18, methods of analysis and selected topics. For this chapter 18, we'll study two sections, independent versus dependent controlled sources, and also source conversion, which we studied in circuit 1, but now will be in AC network. Okay, for chapter 17, direct will go to some examples, 17.2 illustrative examples. Here example 17.1 for network in figure 17.1, calculate Z total. Also calculate determine IS, which is I total. Part C, calculate VR and VC. This circuit 17.1, okay, and we need, as it's required, Z total, IS, and VR and VC. Okay, also it's required IC here. After that, compute the power delivered and find the power factor for the network. Okay. To find Z total, which is the first requirement, we need to simplify these impedances, which is in parallel, to be as one impedance. uh, XC and XL are parallel together. We can recalculate it to find new Z. We will call it Z2, and Z2 with ZR, which is with Z1, which is ZR, will be series together. This means Z1 plus Z2 will give you Z total, okay, and Z1 resistor, it is a resistor. Z2 will be ZC parallel with ZL, these two, XC and XL. We will multiply XC with angle minus 90, as we mentioned in last two chapters, and XL with angle 90, and make the summation. Divide by the summation. XC, it is 2 ohm with angle minus 90, XL 3 with angle 90. You will find the final answer will be 6 with angle minus 90. The summation between them, okay, Z1 and Z2, the total will be 6.08 ohm with angle minus 80.54. Now we have Z total. We can easily calculate IS by dividing E source by Z total. You will get IS. Direct calculation. Be careful. It is direct calculation. Only you need to be careful about using the calculator. Okay, please be careful. The final answer is 19.74 ampere with angle 80.54. Let's go to the third required, which is VC. To calculate, we can calculate VR and VC. Okay, by if you make the combination between XC and XL, this will be Z2, and if we multiply IS by Z1, you will get VR, and if you multiply IS by Z2, you will get VC and VL. Why? Because in parallel the voltages are equal. Okay, now IS by Z1, you will get this answer. Iz by Z2, you will get VC, which is 118 with angle -9. Now, it is required to find IC. Now we have VC and we have XC. Divide VC by ZC, you will get IC. Direct substitution. This is the final answer. To find the power delivered, you have many ways to calculate the power delivered. Either I square by R, because the power in watt consumed in the resistor. Because this we say I square by R. Or you can use another way to find power delivered, which is voltage multiplied by current cosine theta, as we studied in last two chapters. You will get the same answer. For power factor, cosine theta, cosine 80.54. From where we get 80.54? It is theta voltage minus theta I. But also you can find it direct from Z total. Z total 80.54. Does not matter if you calculate cosine minus 80 or cosine 80, because cosine is even function. We found the answer 0.164 leading. Why we wrote leading? After power factor we said we must write leading or lagging. Leading, this means I total, I source, lead V source. Okay, if you notice that IS, it is 80 degree, which is greater than 0 for voltage source. Okay, by this we end the example 17.1. I need from you to go through 17.2. This is a direct calculation. 17.2, also 17.3. Please go through 17.2, 17.3. We will go together for 17.4. The idea for 17.4, I will give you the idea, only the idea, and you go through. We will go another example, 17.5 and 6 and 8. It will be, it has idea, but 17.2, 3, 4, it's a normal example. Type. It's required to find IS and VAB. VAB, which is the voltage here. If we put the voltmeter in point A and point B, what is the voltage? What is the reading will be? Okay, IS easy to calculate. IS, we need to calculate the total impedances. This Z1 R, ZR1 plus ZL will consist for Z1, and ZR2 plus ZC, it will be Z2 as mentioned. And now Z1 and Z2 are parallel. You can use direct formula. Z1 multiplied by Z2 divided by summation. You will get this answer. Okay. Now the part B required VAB. How to find VAB? We need to find VR1 and VR2, and then we'll make a loop. Okay, closed loop. Consists of VAB, VR1, VR2, like here, like here. Okay, we'll make this loop and we'll close loop, which is the summation for a closed loop. If you remember Kirchhoff voltage law, the summation of closed loop equals 0. Now, by this we need to find I1 and I2. I1, which is coming here through Z1, I2 through Z2. If we find I1 and I2, we can multiply by R1 and I2 multiply by R2. We will find VR1 and VR2. How to find I1? which is voltage divided by Z1. Okay, you will get this answer. Voltage divided by Z2. Why divides voltage by Z2 and voltage by Z1? If you go to back to the circuit, because this voltage parallel with Z1 parallel with Z2, and we know that the voltages in a parallel circuit are equal. Okay, after we found I1 and I2, we can multiply I1 by ZR1, I1, sorry, it is written I1, but it is I2, I2 with ZR2. Okay, see here 10 and this 10. This is my mistake, typing mistake, I2. You will multiply and find the answer. After we found VR1, VR2, we can make the loop, which is VAB from minus to positive will be positive. From minus to positive in VR1 will be positive. From positive to minus, the direction of the loop will be minus. And now you will substitute now VAB equal VR2 minus VR1, and you will find the answer VAB. Okay, let us talk now about another example, which is 17.5. This circuit for some network. It is explained here. What is this network? About what? Okay, what is the main point for us to calculate what is required, which is VL. You can read this. Okay, explain what is the circuit for what. Okay, it has R naught, RC, RI, and this capacitor. Okay, since it is all grounded, okay, you can connect it together. It will be one circuit. Okay, and here it's A, determine VL for network in figure 17.10 at frequency of 100 Hertz. After that, we will repeat same steps with 20 kilohertz and see the difference. What will be the VL, V load? Okay, to calculate, we will uh, uh, make it Z1 and Z2. Z1 will be 50 kilo ohms parallel with 3.3, which is this R naught with 3.3 kilo ohm. They are in parallel. It will be Z1, and ZC and ZRI will be Z2 in series. Okay, now we can easily substitute. You will find Z1. Z2, we need to find XC before we add with RI, because the frequency now 100 ohm, 100 hertz. XC 1 over 2 by FC, and now we'll substitute the F by 100. The answer will be 159 ohm. Now we can use this to find the Z2. Z2 become 1 minus J 159. Sorry, here. Okay, now we need to calculate IL. By current divider rule, IL will be Z1 multiplied by I total divided by the summation. Anyone can know why minus here? The minus here come from because the direction of the I source opposite of the assumption. Okay, because this we put minus Z1 I. If you substitute, you will end by this answer: 3.02 milliampere with angle 2.23. How to cancel this minus? Minus in polar form, we can cancel it by add 180 degree in the angle. It's become 2.23 plus 180 degree. Now 3.02 milliampere and the angle 182.23. This is the first IL with 100 the frequency 100 hertz. Now we will multiply IL by Z2. You will get VL by substitute. Okay, this is the answer. Part B. For part B, we will use the frequency to be 20 kilohertz, and the XC will find will be 0.796 ohm. If we substitute Z2 will be similar in R but different in XC. Here it was 159, now 0.796. Okay, we'll do same thing, same procedure. Z1 multiplied by I is summation for Z1 plus Z2. You will find the final answer for the current 3.02, and the angle after changing the minus, replace the minus by 180, becomes like this. Okay, if you multiply IL by ZR, or sorry Z2 يعني, okay, you will find VL 3.02, the angle 180. You can see the answer almost the same, because this question 3 compare the result of part A and B. You will see the result clearly indicate that the capacitor had a little effect on the frequencies of interest. In addition, note that most of the supply current reach the load for the typical parameter employee. Now we'll go to example 17.6. All these examples, it's not a new subject, only example about the combination between series and parallel. يعني this in the exam will not be the question will not be difficult. It will be inshallah easy. يعني only you need to practice as we did in circuit 1, series and parallel circuit. Here we will do another series with parallel combination, but with AC. All the rules applied in the circuit 1 will apply here. Okay, this example, another example with two current source. Okay, but here before in circuit 1, if the current source 6 ampere and the opposite direction 4 ampere, we subtract them 6 minus 4 and finish. But now here the source current 6 milliampere with angle 20. You need to consider angles, and the opposite direction 4 milliampere. Okay, be careful about this. The required determine the current I and find the voltage V. How to find I? We said subtract, but with angle. See this? Okay, you will find the final answer, not 2. It is 2.626 milliampere with angle 52.4. Okay, and find voltage V. Where is voltage V? In the circuit here, voltage V. We need to find the current going here and multiply by R3. You will find V which is required here. Okay, now we can say Z1, which is 2 kilo ohm with 6.8, 2 kilo ohm with 6.8. It is missing, typing missing parallel. Put parallel symbol here. Okay, 2 kilo ohm parallel with point, sorry, here with 6.8 kilo ohm. Okay, and Z2, which is summation, R2 plus XC. Sorry شباب, it's I here. This is I, not subtraction. It is required. This is the symbol I. It's written in this branch. We need to find I in this branch. Okay, which is this, how to find it. Okay, after we find Z1, which is R1 parallel with R3, and Z2, which is R2 series with XC. Okay, now we can redraw the circuit by this circuit. I total 2.626 with Z1 and Z2. We know Z1, this Z1, and Z2 series branch. Now, if we find the current through Z2, this means I, which is same as in the original circuit. How to find this? By current divider rule, the easiest way to find I in this branch. Okay, if we need I in this branch, we will multiply I total by Z1 and divide by summation. You will substitute and you will find the I, this value. The I going through Z2 similar to I here in the original circuit. Now, we have I, and if we multiply by Z2, we will get voltage. This voltage, it is similar, I mean this voltage in this branch will be this similar voltage in this branch because it is parallel circuit. If we find the voltage here, we will say equal the voltage V. And we can direct I multiply by Z2, you will get V. I multiply by Z2, you will get V. Okay. I think this is the last example will go, or yeah, 17.8 will be easy. Direct calculation will go only about 17.7. Compute I and I1, I2, I3, Kirchhoff voltage, so current flow by showing that, verify, and find the total impedance. Okay. Now we have the circuit. We can add R3 XL2 with XC to be one impedance will be Z3, and R2 XL1 to be one impedance, and R1 will be Z1. Okay, as we did here. Now we can calculate direct the total impedance or find the admittance, as we studied in chapter 16 parallel circuit. Y total equal y1 plus y2 plus y3, which is 1 over z1, 1 over z2, 1 over z3. If you go through the calculation and substituting, you will find the admittance will be 0.316 Siemens with angle minus 18. How to find now I1, I2, I3? You will, because the voltage is equal, voltage source equal V1 equal V2 equal V3, we can say V1 divided by Z1, you will give you I1. V2 divided by Z2, you will get I2. V3 divided by Z3, you will get I3. Okay, as shown here. Okay. Okay, and I total it is a voltage source with the admittance. Now we need to verify that the summation of I1, I2, I3 equal this. Substituting, you will try to calculate this terms. You will find it equal I source. The last requirement is Z total. How to find Z total? 1 over Y total. It is all direct substituting. Only you need to know the formulas and you understand the chapter 15 and 16 for series and parallel. And this chapter is a combination. Okay, try to go through 17.8 at least for your studying. You need to go through the solved example. Okay. Okay, now we'll go to 17.3, which is called ladder ladder networks. Ladder networks mean Z5 with Z6 series, both of them parallel with ZR, all of them series with Z3, and we'll make this combination with Z2 become parallel, and then with Z1 series. This means series, parallel, series, parallel, series, parallel. Okay, and this is the formula. You can write it like this. We can say Z total double prime, which is Z5 plus Z6, and both of them parallel with Z4. Okay, if we added series with Z3, we can call it Z prime total. And Z prime total for this impedances parallel with Z2, and all these impedances series with Z1, and this called Z total. Okay, to find I total, you will divide V total divide by Z total, you will get I total. I3, which is going through impedance Z3, you can apply current divider rule. Assume that the impedance here Z prime total, and this another impedance in parallel. I3 Z2 multiply by I1 and divide by summation. If you need to find I6, which is I5, okay, because I5 Z5 and Z6 series, you will say Z4 multiply by I3, which is coming here from here, is considered as the total coming, and divide in this branch and in this branch. You will multiply I3 by Z4, divide the summation. Okay, and this showing you figure 17.22 show you the what we did. Okay, this circuit, if you see this circuit anywhere, it's called ladder networks. Now we'll start talking about chapter 18, two section only. The first section 18.2, independent versus dependent controlled sources, only to show the difference between independent and dependent. Before in circuit 1 or circuit 2, we say the symbol for current and voltage. This is the voltage DC and the voltage AC, and this is the current DC, current AC. Okay, this called independent source. It does not depend on anything else. Okay, but now we'll show the symbol for dependent source. It depend on something else. Okay, when you show this symbol, this is for voltage and this is for current, similar to AC, but you write constant next to the voltage or constant next to the current, this mean independent source. But nowadays, many books use another symbol, new symbol for showing that this voltage or current dependent source, which is this symbol. Okay, this for voltage mean dependent source voltage, and this dependent current source. Only you need to know in this section the difference between the dependent and independent source. We'll uh, we'll go through another section, which is source conversion. Sorry, conversion. If you remember in circuit one, we studied source conversion. If you have voltage source series with the impedance, you can convert it to current source parallel with the impedance. Okay, or the opposite. If you have current source parallel with the impedance, you can convert it to voltage source with the series with the impedance. Okay, we'll study independent sources and dependent sources. For independent sources, this is one example. Convert the voltage source in figure to current source. We have 100 ohm with angle 0, and this is our impedance. We can divide 100 by this impedance, as we did here, and find the value of the current source. And it becomes I equal 20 ampere angle 53.13, and parallel with the same impedance, same value. Another example, we have a current source. We need to convert it to a voltage source. First, we will make the parallel between XL and XC and find the Z. If you apply it here, ZC multiplied by ZL divided by summation, you will find the final answer 12 with angle minus 90. If you say 12 with angle minus 90, you can say it is capacitor, because this, when we convert it to voltage source, only we draw capacitor with the 12 ohm. And the voltage, how we found the voltage, we will multiply the current with the Z we found. Okay, the current with Z, you will find this value. Okay, and this is the final answer. For dependent source, you need to be careful about the value of the voltage or current. Okay, like this, convert the voltage source in figure 18.8a to current source. Now we have this dependent source, which is 20 constant multiplied by V. Okay, and this is our impedance, and V is given here 120, depend on source, the value of this source 120. This means we need to multiply 120 multiply by 20, because the relation between 20 and V is multiplication, and divide by Z to find the current value. See here, I equal E over Z. What is E? It is 20V divided by 5 kilo ohm. 20V, this means 20 multiplied by 120, the angle 0, you will find 2.4 kilovolt, and divide by 5 kilo, it will be cancelled, and the final current will be 0.48 ampere. And we redraw this circuit to be current source, dependent current source with value of 0.48 ampere, parallel with the impedance 5 kilo ohm, which is same value here. Nothing changed for the impedance. Last example in this chapter, to convert the current source to voltage source. Same thing, we have this current source depend on I, the value of I, and I coming from another source, which is 80 milliampere. Okay, how to find the value? We will multiply 80 milliampere by 100 and then multiply by Z. You will get the value of voltage, like here, I V Z. What is I? It is 100 by I. And what is I, variable I? It is 80 milliampere. We multiply all, we will get 320 volt with angle 0, and we need to redraw the circuit. Voltage source, dependent voltage source, series with the impedance. And by this we conclude our lecture about chapter 17 and 18.